All right, now we're going to continue to talk about logarithmic functions. We were talking about last week about inverse functions, and there was a couple ways to talk about inverses. The first thing I introduced was that two functions are inverses of each other if they're symmetric on this y equals x line, this diagonal line. Or we can verify if two functions are inverses of each other using composition and they simplifying to x, right? How did we know? That was just to check if two functions were inverses. And then we said, well, how do we know if a function even has an inverse to begin with? And that was with this definition that we needed to know if it was 1-to-1, which as long as you know it's 1-to-1, you know it has an inverse. But how do we know it's 1-to-1 to begin with? We had a few definitions, but ultimately came up with the horizontal line test. As long as no vertical line intersects the graph more than once, then that is a 1-to-1 function. But don't forget, the equation has to first pass the vertical line test, which defines it to be a function, and then you can check for a 1-to-1 function. You cannot check 1-to-1. You can't use the horizontal line test without using the vertical line test first, right? So you have to be careful because there are some equations that pass the horizontal line test but fail the vertical line test. So you must pass vertical before you can check your horizontal. Now, logarithmic functions are actually inverses of the exponential function. Because if we look at an exponential, well, we know it's a function because it passes the vertical line test. Since it passes the vertical line test, I can now check the horizontal line test, which it also passes the horizontal line test. And I know here it might look that it's flattening out, but remember, this is the horizontal asymptote for my exponential function, which means this part of the graph continues approaching the horizontal line forever. It never goes completely horizontal. It just keeps getting closer and closer to that horizontal asymptote. Now, we did just say for functions to be inverses of each other, they need to be symmetric over this y equals x line. So if a logarithm is the inverse of an exponential, then that means they should have symmetry over this line. And if they do, then this is the way a logarithm would have to look. I'm trying to make this as symmetrical as I possibly can, but I think you'll get the point. But this is the idea of what a logarithm is going to look like, where the exponential grows really fast, well, the logarithm grows really slow, and you can see what the shape is going to be. But remember, we talked about how if you do symmetry over this line, not only are you reflecting the graph, but you must reflect the horizontal asymptote again as well. I mean, if you reflect this horizontal asymptote, it actually becomes a vertical asymptote, and that's how you can see the logarithm then approaches this vertical asymptote forever, and then gradually grows slowly as it goes further to the right. Now, this change, even though we're just looking at the horizontal becomes a vertical, but what's really happening is we're taking the domain of the exponential and it's becoming the range of the logarithm. And the range of the exponential is becoming the domain of the logarithm, because we said during class that when you're dealing with inverses, the domain and range interchange between each other. So a quick way to see that is we all saw that exponentials intersect this point, right? The parent function at least, intersect this point at 0, 1. If the domain and range are interchanging, then that means this y value becomes an x and the x becomes a y. And that is this same identical point that exponentials have. There's a similar point that all logarithms have, and it's at this 1, 0 point. Because we're interchanging our x's and y's. And we can see that happen with this point. And this is a general shape of what a logarithm is going to look like. It's going to change just the same way the exponential, right? When we change the exponential, sometimes it grew faster. If it was between 0 and 1, it had a different shape. But the exponential and logarithm we're going to focus on is the exponential that has a base greater than 1. And we're going to do the same with the logarithm. But now, let's see what a logarithm actually looks like. So, notation. This is what a logarithm looks like. It has y equals log base b of x. Now, this is the first time where you have everything we've looked up to this point, every function we've looked at is either had some variable, an exponent, that could either be the exponential, the polynomial, rational. It was all coefficients, variables, and exponents. The logarithm is the first function that has words in it. And that's due to the fact that we don't have a very straightforward operation when it comes to a logarithm. Now, when you see, for example, x squared, you have your variable and you have an exponent. You understand that operation of a power of 2. Same with addition, subtraction, division, multiplication. Those are all general operations that we understand what they're doing. And we understand what it would do to a variable, right? We put a variable in the absolute value, we understand the operation of what absolute value is doing. We put a variable in a denominator, we know it's dividing. We put a variable inside of a square root, well, we know how to simplify square roots. When we apply log, so the way you would read this, the way you read is log base b of x. That's how you read this logarithm. Log base b of x. And again, the word log there is just to indicate what type of function we are dealing with. Like we talked about before, why is it called an exponential function? Well, that was because the variable was in the exponent. Why is it called an absolute value function? Because the variable is in the absolute value. Why is it called a rational function? It's because the variable is in the denominator. And all these things of why we gave particular function names is really due to the operation in question. And the only operation we have here is the log. There's nothing here that's telling us what we need to do. So for that, the logarithm's pretty interesting. Again, it's the first one that actually has a word or letters inside other than our variables and coefficients and constant terms. This is the first time we have these letters or a word full inside of our function. Now, once again, this is written in equation notation. You can also write this. So I'm going to put here on the side, I'm going to put or above it. Or you can write this as f of x is equal to log base b of x. It's just sometimes nicer to always go back to what a function is equal to. right? It's equal to y, what your f of x notation is. Now, the logarithm, as I was saying, when you see log base b of x, there's no immediate operation. If I were to put a number for x, there's nothing really telling me about what to do with that variable. Where if I have an x squared and if I were to plug in, let's say 2, I know how to simplify this. Same thing if I had absolute value of x. If I plug a 2 inside, I know this is equal to 2, right? I know how to handle that expression or equation or function. The logarithm is the first one where you don't necessarily know the operation of what a log does. So there is an equivalent form of finding or evaluating a logarithm. And this is the equivalent form that you're going to use all the time. And instead of writing the logarithm in using log, is the logarithm's also equivalent, or maybe I'll say in words, y equals log base b of x is equivalent to, I'm going to write this in red because it's really, really important, to b to the y is equal to x. Now you're wondering, wait, that looks like an exponential. And again, it's because we said logarithms and exponentials are inverses of each other. Now, this is how we would write a logarithm before. Instead of using function notation, I can use equation notation instead. So y is equal to a to the power of x. Now, we haven't started talking about how to find inverses of a function, but the big part of it, remember I said there needs to be reflection on this y equals x line. So if I'm reflecting on this line, that means I must be changing my domain and range. And I'm actually interchanging between my domain and between my range. But let's not forget, when we're talking about domain, it has to do with all my x coordinates. Range has to do with all my y coordinates. So what ends up happening is all your x's for one function become nothing but y's for its inverse. And the y's of the original function become the x's of the inverse. So what you're really doing to find your inverses is you're interchanging x and y between each other. But that's also interchanging the domain and range. So if I look at this y equals a to the x, then that means that my inverse, if all I'm doing is interchanging x and y, this inverse should be equal to x equals base of a to the power of y. If we're following this idea of to find an inverse, there needs to be reflection on this y equals x line. So that means all we're really doing is your x becomes your y and your y becomes your x. And if you notice, this x equals a base to my y power is exactly what I have written here. It's just instead of a, I wrote b. I have x equal to some base raised to the y power. This is what a logarithm looks like. But to give it its own, I guess, identity, instead of writing it as x equals b to the y, we write it as log base b of x to write it in a formal notation. But we don't think about the logarithm usually as log base p of x. We want to rethink it as this we call the exponential form of a logarithm. So this exponential form of a log. And this is how you would evaluate your logarithm. And then you just rewrite it back into your logarithmic notation. Now, a couple things to point out, right? We are interchanging or changing. Our domain becomes our range becomes our domain. Now, if we look at the exponential function, we knew that it only existed above the x-axis. So when it came to talking about the range of an exponential, it was anything from 0 above. But that idea of the range translates to the domain of the logarithm, meaning if you notice, the logarithm only exists from this vertical asymptote of 0 all the way to the right. So we can see that when it comes to my logarithm, a couple things to note. The logarithm x always has to be greater than 0. But to help add some terminology, the x, the same way when you think about radical, inside of the radical is known as a radicand. The bottom of a denominator is known, the bottom of a fraction is known as a denominator. Well, the inside of a logarithm is known as an argument. So you might hear me use this word where the argument / domain of a logarithm has to be strictly greater than 0. Cannot be equal to it, strictly greater than 0. And just like the base for an exponential, the base for a logarithm also has restrictions. It's either going to be bigger than 1 or it's going to be in between 0 and 1. It can't be equal to 0. It can't be equal to 1 because it will not have the behavior of a typical logarithm. But before we get into looking, well, we kind of already see what a logarithm looks like. But before we actually graph using a table, because that's where I always like to start, I want to work with evaluating the logarithm, because every other type of expression, the moment you plug or function, the moment you plug in a number, you know exactly how to simplify it. The logarithm is the first type of function that it's not very straightforward in terms of the evaluation. Like I said, if you see a number inside of absolute value, you know what to do. Inside of a square root, you know what to do. In a denominator, you know what to do. As an exponent, you know what to do. But here, the fact that we have to rewrite it to process it as an exponential and then put it back into a logarithm is where it can create some confusion. So let's do a couple examples so we can see this. And then we're going to look at a graph. So we're going to evaluate. To start, our goal is to find log base 2 of 16. Now, like how we said, I don't know what this is equal to, but I don't know what to do. This isn't 2 to the power of 16. This is the argument of the logarithm of 16. So if it's not a power and the 2 is a base, again, don't try to do 2 to the 16th power. That's not how these work. What you're supposed to do, like I said, is rewrite this into its exponential form. Now, to look back at this exponential form, and I will highlight it because it's the most important property when it comes to a logarithm. If you notice the base, when it converts to exponential form, it's still a base. but the argument becomes the output, and your y becomes the input, and that becomes the exponent. So let's see. Right now, my 2 is my base. I write 2. But then my argument has to give me what it's equal to. But the output becomes the input. So what's really happening here is I need to find the way to really think about this logarithm is what power can I raise 2? What power will this 2 need to give me 16? Now this I can process because I understand how exponents work. In the logarithmic form, I couldn't really understand what to do. Now here I can just say, oh, that's 4. Because 2 times 2 is 8. Times 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Or, I don't know why I wrote 2. But to evaluate this logarithm, it's equal to 4. Let's do a couple more. For example, log base 7 of 1. Same thing. Don't know what this is equal to, and I don't know how to process it because this is not to 7 to the power of 1. If I rewrite this, well, my 7 is my base. I need to find the exponent, and it has to be equal to 1. Now, this goes back to rules that we looked at before for exponents. Whenever I raise anything to the power of 0, I'm going to get 1. And that's just a common rule of thumb, a common exponential rule for one to remember. Now, the problems that get tricky, and it's everybody's favorite, is when we start introducing fractions. Because even when I rewrite this exponential, my base is 4. I need to find my power. That's going to give me 1 over 64. Now this is the part that gets tricky because normally exponents make numbers larger. 0 is the only one that makes everything 1, so it might be making some numbers smaller or most numbers smaller. But to convert a 4 into some decimal or some fraction, that's a little bit more challenging. But we have to be able to analyze the problem. If I, for example, just ignore the 1 for now, if this was just equal to 64, I can say, well, I know 4 to the power of 3 gives me 64. 4 times 4 is 16 times 4. 16 times 4 is going to give me 64. But that's not 1 over 64. So I need to figure out a way that I can rewrite this 64 in a numerator, or I can rewrite this 4 to the third, which is just a regular 64, back in the denominator. And a rule of exponent that we've talked about is negative exponents. Negative exponents allow us to rewrite a number as a fraction, which this will become 1 over 4 to the third, which will then give me that 1 over 64 I was looking for. So those are the ones that get pretty tricky, right? But the idea is this rewriting into exponential form. That's what allows you to be able to evaluate / simplify a logarithm. And you have to get comfortable with this because whenever you're evaluating, you have to be able to think about it as exponential and then go back to the logarithm and you want to do that all quickly. This was 3 separate examples. But when it comes to graphing an exponential, which is just one example, I would need to do this same process 10 times for one problem, right? That's what we always end up coming across, where before there would be a problem that we would do a few examples, but then we moved further into the content, and sometimes those few examples were just one part of a larger problem to solve. So now let's see, even though we know roughly what a graph should look like, let's really focus on using a table to really get the exact points for a logarithm. Now let's not forget our argument, which is the number that's right next to your logarithm and above the base, is your argument has to be strictly greater than 0. Now, everything we've done to this point for being able to graph any equation, any function, has always been using a table. And when it came to this table, you are allowed to choose any value and then find its corresponding value. But after a while, we really did stop thinking about choosing values from one particular column. We stuck to only choosing our x's. But for the logarithm, this is the one time that you probably don't want to be using starting with choosing your x's. You actually want to choose your y's. And let me give you a quick example of why that's true. So if I just started, 3 is a perfectly common number that we would use for our x when we're looking at quadratics, polynomials, rationals. 3 was a perfectly good number to use. Now, if I try using 3, that would mean I have to find f of 3, right? Which gives me log base 2 of 3. Now, I did say I don't know how to handle this. I have to rewrite this into its equivalent form, which would be the base of 2, still a base, but then the argument is what we want the base to some power to be equal to. So I need to try to find an exponent that's going to give me 3. Now, does this exist? Yes. And remember, a negative exponent just turns this into a fraction. 0 turns it into 1. A number bigger than 1 just makes 2 even larger, right? The number 1 keeps it 2. Number 2 makes it 4. It's already larger than 3. So that means this has to exist between the power of 1 and the power of 2. But there's no straightforward way for me to find, at least by hand, 2 to what power is going to give me 3. It's not like the previous example where I can use negative exponents to try to manipulate it. And this is where we get stuck, because it's tricky to find an answer like this. Whereas if I were to choose my y value, which I know we haven't done in a long time, but even when we were checking the intersection for the horizontal asymptote for rational functions, I said just take your horizontal asymptote, which was some y, and replace your entire function notation with it. So that means I'm replacing my entire f of x with the number 3, as you can see here. And this, I didn't plug into my x, right? I can always choose one variable, either be y or x, and then find the corresponding one. Now, I'm going to rewrite this into that exponential form that we like. My base still remains a base. My exponent comes from my output, which is 3. And then that is equal to my argument. But here, there is no thought I need to put in. I know exactly what 2 to the third power is. 2 times 2 is 4, times 2 is 8. Bingo. I didn't have to do anything. Some other common numbers we use. 2, 1, 0, -1, -2. All very common numbers that we choose for x. But another example, 0 is a very common number we use for x. But we remember that 0 cannot be used in our argument. So there's so many things to think about when it comes to a logarithm, when you're graphing it, for choosing your x versus choosing your y. And that's why for logarithms, I always emphasize just choose a y value instead of an x. And just because it says f of x, that does not mean it's not equal to some number. It's just a different notation. But we will take this number and completely replace our function notation to give us 2 equal to log base 2 of x, which then I rewrite into its exponential form. 2 to the power of 2 is equal to x, which will give me 4. And then I can keep doing this. 1 is equal to log base 2 of x. That's going to be 2 to the power of 1, which is equal to 2. 0, once again, I rewrite base 2 to the power of 0 is equal to x. Anything to the power of 0 gives me 1. -1 log base 2 of x. Logarithm is perfectly okay with y values being negative. This is just going to be 2 to the power -1 is equal to x, which then we use our rule of exponents to rewrite this as 1/2. And last but not least, log base 2 of x. That's going to be the base of 2 to the power of -2 equals to x, which I know I can rewrite a negative exponent as 1 over 2 squared, which is going to give me 1/4. And if I notice here, these are definitely some numbers I never would have picked for 1/2. But 3 would have been, but I wouldn't have been able to find the actual value. So for logarithms is why I choose the y coordinate, which is my f of x, to be able to find my corresponding variable. Now, we have all these ordered pairs. Let's try to sketch what the logarithm looks like. So to start, try to make it a big 1, 2, 3, 4. 1, 2, 3, 4. And then here. Now, for the sake of time, remember we said 2 things. Our argument, which is our x, cannot be equal to 0. It has to be strictly greater than 0. So that means is why we have a vertical asymptote for the exponential. I'm writing it in bold, so I don't want to make tick marks, which I guess I can. I'll just do it. Because this is my vertical asymptote, which we talked about when we introduced this concept of inverses, how exponentials and logarithms are inverses. So, but not only do you find the symmetry or reflect the graph of the exponential, but you also reflect and copy the horizontal asymptote, which becomes the vertical asymptote for the logarithm. Now, let's look at some points. 2, 3, 5. Well, let me write a couple more. So 1, 2, 3, 4, 5, 6, 7, 8. Now, our first point, we weren't able to find. We don't know 2 to what power gives us 3. But we know when x is 3, when x is 8, y is 3. So 1, 2, 3, 4, 5, 6, 7, 8. And we'll go up 1, 2, 3. So that's our first ordered pair. Then we have 4 and 2. And then we have 2 and 1. Those are points we're getting. We also have 1 and 0. Again, this used to be that 0, 1 for exponentials, but this becomes that 1, 0 for logarithm. And then we have 1/2 -1. And then 1/4, right? Because 1/2 is about here. 1/4 is half of that, which is at -2. And if this keeps going, right? If I choose -3, -4, -5, the logarithm is going to just continue getting closer and closer to the vertical asymptote. Let me try to fix this. And I'm trying to make it as best as I can. There we go. That's a rough idea. Again, it does continue downward, but it doesn't go completely vertical. Sorry. It doesn't go completely vertical here. It does get gradually closer and closer to the vertical asymptote. Similar behavior when it came to rational functions. Now, this was just when our base is 2. Let me show you a couple different versions. Now, if you notice, we have log base 2, log base 3, log base 4, and then this weird that says log base e. Now, if we go back, like I said, the logarithm has either a base of bigger than 1 or in between 0 and 1. Now, this is the shape for all the exponentials that are bigger than 1. When they're smaller than 1, they go in the opposite direction. But we're going to focus on only the ones bigger than 1 for now. Now, if you notice, they all have this similar behavior. And then once again, they all intersect this 1, 0. And we can see that they get really, really close to that vertical line. It might look like it's crossing it, but when you start zooming in, you start seeing that separation. Now, this point and the vertical asymptote will help us when it comes to sketching this graph. Now, like I've said before, I don't like using a table every single time, but we do want to have a rough idea to be able to sketch our graph. We're not going to have all these points, but maybe there's some points that we can use, right? For example, 1, 0 is a great point to be able to use. Now I just realized I forgot to say one thing. If you notice, let me turn all these other logarithms off. I have 2 examples here. but they both are completely overlapping each other. And the reason for that is because these two logarithms are exactly, you can see how it goes from blue to green. And the reason why they're exactly the same is because E, the same way I'm sure people have heard of pi, is 3.14. Well, E is also a very special number. E is about 2.7. It's an irrational number, but we approximate it with 2.7. So that means it's bigger than 1. That's why it still has this same shape as all the other logarithms, right? All the same overall shape. Now, why does this look exactly the same in green? And that's because when the logarithm has a base of e, we call this the natural logarithm. The same way an exponential, there's also a natural exponential. And that's an exponential that has a base of e. But again, as long as we know that e, let's not forget, make a quick note. I'll just put it anywhere. E is approximately 2.7. And that's what it allows you to still graph it as these other graphs. But like we've always done, we start with a table to get a rough idea of what the graph is, but then we go and sketch it. So let's look at some sketches for a logarithm. So for example, and we're going to sketch using transformations, just like how we were doing with the exponential. Because making a table just takes too long. So with our first graph, let's try to graph log base x of log base 3. Sorry, f of x equals log base 3 of x plus 3 minus 2. Now remember, I always had this inside and outside for my transformations. The exponential one was the only one that looked different because there was nothing that looked inside. But I told you to interpret the quote-unquote inside of an exponential is the exponent. The outside is whatever's at the level of the base. Now the logarithm, it's a little more, I wouldn't say obvious, but it's much nicer to find or differentiate the inside from outside, because here we have parentheses for, remember, this is known as our argument. So we have these parentheses that really do illustrate that inside, but it's also given as the argument, and other values are known as outside. So if we were to do a quick sketch, so I'll do it here on the side. I'll do a quick sketch of this. I'm not looking for perfect graphs. I'm also not looking for sloppy ones. But we start with our parent function. So the parent function here is log base 3 of x. So we graph log base 2, but like I always said, as long as it's bigger than 1, they all have this same overall shape, which means they have this vertical asymptote, and I'm going to draw it just a solid blue line for my vertical asymptote. And they all have that point 0 and 1. Put that right here. And then just create a rough sketch of my graph. If you want more points, you're more than welcome to use them. But like I said, this just a rough sketch of a logarithm. Now, the difference when it comes to, or not the difference, but similarly, when we were doing transformations to the exponential, we had to be careful for our horizontal asymptote. Now, for the logarithm, you have to be careful for this vertical asymptote, because if you move this vertical asymptote up or down, it stays in the same place. You stretch it horizontally or vertically, stays in the same place. If you move up, you move down. If you stretch it vertically, shrink it vertically, this line doesn't change at all. It only changes when we shift left to right, which if you remember, when you're adding something inside the logarithm, you have to shift it in the opposite direction of what you naturally would think. So usually you might think, oh, let me actually move this a little bit over to be able to fit in my graph what I'm trying to do. I'll put this here and this here. Again, the reason why I'm doing that is to give myself room, because this has to shift to the left 1, 2, 3 times. So that means my new asymptote is at where x is -3, because it shifted 3 to the left. But so does my point. My point also has to shift 3 to the left, which is now here. And again, the overall shape isn't changing. It's just shifting. So you can see here, it just shifts to the left. That's all that's happening. Remember, the only time the vertical asymptote shifts is it when we choose left to right. Now, if you're asking what happened to my first transformation, well, x doesn't have any other coefficient other than +1. So there's no stretching or shrinking or reflecting. My 3 moves it to the left. There's nothing multiplying outside of the logarithm. So no reflection, no stretching or shrinking. But there is a -2, and that shifts your graph down by 2. But since we're not stretching or shrinking, the graph just has to move down. But this entire time, if you notice, I stopped talking about the vertical asymptote. Oops. But you have to be careful, because if you see here, I actually sketched my graph as it was intersecting the vertical asymptote, where the vertical asymptote never shifted. It still is in the same place. It only shifted at the very beginning. So when you're sketching these, you want to be very careful and make sure you're not drawing a sketch that is accidentally intersecting your asymptote when it's not supposed to. Now let's do one more example to not make this video be too long. So here, let's look at h of x is equal to negative log base 2 of x minus 2 plus 1. So vertical asymptote is still in the same place. That doesn't change. I have my graph. My parent function here is log base 2 of x. That's my parent function, log base 2 of x, which means there's a point here at 0, 1. And once again, this is my rough sketch of the graph of my parent function. All right, gradually grows, gradually goes down. There's no coefficient here to stretch this lower, or stretch it higher, or shrink it. But there's this -2 that has to move the graph over to the right by 2. Remember, you have to make sure you're shifting your vertical asymptote as well. This then causes the graph to shift 2 units to the right as well. And then you have your logarithm. Now, this is where things change a little bit. Because now we actually do have something outside. Remember, this is the last one we take care of. This is my inside, then I work outside. A negative outside does a reflection on the y-axis. And that's my reflection. And that 1 just moves it up 1. So it's going to move up to here. And I'm just going to copy my last one, which is the purple one. Paste. Again, all the transformations for the most part are the same. We just need to remember these small nuances of each one of the graphs. Now, there's a lot of properties and ideas when it comes to logarithms. So those are things that we will discuss on our next video. But if you have to replay this again, I try to keep it as short as possible. But once again, I can't emphasize this enough. There are other rules and properties for logarithms. But this, whoops, I erased everything. This is single-handedly the most important, which says how you treat a logarithm. You have to rewrite it into an exponential form. So keep that in mind, and I'll create another video talking about the different properties that logarithms have.